So in this problem, this is a temperature characteristics of resistors problem. Problem 2.6. Problem 2.6. So we've already looked at this problem. I'm going to read it out now, and then we're going to figure out what we have to do with it. So this problem states that a light bulb has a filament whose resistance is characterized by a temperature coefficient of alpha equals 6 times 10 to the minus 3 degrees Celsius to the inverse. The bulb is connected to a 100-volt household voltage source via switch. After turning on the switch, the temperature of the filament increases rapidly from the initial room temperature of 20 degrees Celsius to an operating temperature of 1,800 degrees Celsius. When it reaches its operating temperature, it consumes 80 watts of power. So the first thing that we're going to do with this is, I call it data extraction, because there's a lot of data in this problem, and we have to be able to pull it out. So the first bit that we're going to do is we're going to do 3 cases here, because I see 3 different cases. I see a cold case, and a cold case means that the temperature equals 0 degrees Celsius. I see a room temperature case, where temperature equals 20 degrees Celsius, and I see a hot case, where the temperature equals 1,800 degrees Celsius. So inside of each of these cases now we're going to pull out the data that we have. So the problem states that we have 100-volt household voltage. So voltage is going to be the same at any temperature. So we're going to use this as a nice equals 100 volts across the board. Well, it's V equals 100 volts. Cool. And now we're going to look at the next thing. What else do we have? It says we have an alpha temperature coefficient of 6 times 10 to the minus 3. So by definition, a coefficient is not, it stays the same. So it doesn't change. So we're going to have an alpha here. I got to learn to draw alpha better. Alpha equals 6 times 10 to the minus 3, 6 times 10 to the minus 3 degrees Celsius inverse. And we're going to go that across the board. 6 times 10 to the minus 3 degrees Celsius minus 1, that's a 3. And we have an alpha over here equals 6 times 10 to the minus 3 degrees Celsius minus 1. All right, so what other data do we have? It says that when it reaches the operating temperature, which is 1,800 degrees Celsius, it consumes 80 watts of power. So we know that this wattage equals 80 watts of power. 80 watts. Or remember, this is power, so let's use that instead of watts. So power equals 80 watts. Wow. Anyway, so we don't know the power for each of these. Power. Okay, that's okay. We're gonna get there. What else do we have? It doesn't say. We're gonna look back at our equation number 1. So our equation number 1 is R equals R0 of 1 plus alpha t. And in this, we have temperature, which is the different cases. We have an alpha, which is each of these. We have 1, which is nothing. And then we have an R0, which is the resistance 0. So it's like the part of the equation that changes the resistor for the actual resistance. So this is actually a coefficient across the board too, but we don't have it yet. So let's do R0 equals R0 equals R0 equals. And then what else? Oh, we don't have the R's for each of these either, because they're going to change. Because remember, if this is changing with temperature, the R is going to change. So these are going to be 3 different ones that we don't currently have. R equals. All right, is there anything else we don't know? P, we don't know current at any of these either. So we're going to do a current equals, a current equals, a current equals. So just for show here, I'm going to pull out the ones that we know are going to be changing. So we know I is going to change. We know that R is going to change. This is going to be a constant. We know that power is going to change. We know that's a constant. That's dependent, and that's already solved. It is going to change, but all right, so let's just put it just because we know it is going to change, even though we already have it solved. So we know that's going to be the same for all of these. And this is just a quick way to look at, to make sure that we're not solving one, because if we solve R0, we know R0 is going to be the same across the board. We don't know, though, that if we solve R, that is not going to necessarily be the same across the board. So we get R, this one, and power. We get these temperatures here, too. Again, this is just for kicks, just to show you. All right, so I think we have all the data pulled out of the problem that we need, so let's begin trying to solve it now. So the first question that we have on here, and this is going to be our first relevant equation, so we're just going to keep that out of the way for right now. The first thing that we're trying to solve here, I just noticed that was a little off center. Sorry, guys. Is find the resistance A equals find resistance, find R at 1,800 degrees Celsius. So let's just look. Do we have R for this? We already pulled through. We don't have R, so we will have to solve this one. So R, what do we have? What relevant equations do we have? We have what? P equals the equation for power. P equals IV. What other equations do we have? V equals IR, right? So if we're looking for resistance, which is this one, we need current and we need voltage. So we already have voltage, but we don't have current. So we're going to need to solve for current, because look, there's two unknowns in one equation. We can't have that. We can't solve for that. So let's go back over here. If we have power, power equals 80 watts. We do have that one. I, we don't have. V, we do have. So we're going to be able to plug this in as 80 watts equals I, and then V equals 100 volts. And so if we solve that, we're just going to do 80 divided by 100. We're going to get 0.8 equals I. And that's in amps. Let's just write that down just to be, change it over. Equals 0.8 amps. Okay? So now we have 0.8. We're going to write it up in here. I equals, actually let's write it in red because we solved for that one. I equals 0.8 amps. And now we're going to plug that 0.8 amps in over here so we can solve for R. So V we already have again. V equals 100. So 100 volts equals I equals 0.8 amps times R. And so if we solve that out, 125 equals R. And remember that's in ohms, so we're going to do R equals 125 ohms. R, I'm going to pull it up here, because remember this is only for the 1,800 degrees Celsius case, because that's the only one that we had power for. That's the only way we could solve this. So this is only going to be for this one. So that's 125 ohms. So that looks pretty good to me. That looks like the first R. So let's continue on here. What is, I'm going to put a line here. There we go. And now we're going to try to solve for B. And what is B? B says determine the filament resistance at room temperature. So this is find R at 20 degrees Celsius. And so we're going to go back up to the room case here. So find R at 20 degrees Celsius. So again, we don't have power for this one. We don't have I for this one, and we don't have R. So we can't do this one because all we have is voltage down here, and V equals IR. Well, we have V, we don't have I or R, so we can't use this one. So what do we do then to solve this one? There must be another equation, and there is. We have this equation up here, which was given to us early on from the book, which is essentially the temperature characteristics of resistors. So what we're going to do here is we're going to write this equation down because we know we're going to use it somehow. Equals R0, 1 plus alpha t. Okay, so let's see if we can solve this one. So let's use the room case again. So for room case, R equals R0. We don't have R or R0. So how do we get this? Well, remember we said R0, it's not in a box right now, in a red box, so R0 is going to be the same across the board. So it's like a little puzzle. If we solve it over here, which should be easier because we have a lot more data, it'll percolate across. And then if we have it here, we can use it to solve the other part. So let's do this R0 over here first. So we're actually going to solve, first one, we're going to find, as a subpart of this, find R0 at 1,800 degrees Celsius. So for R0, that should be easier to be able to be done. So for this one, we're going to have R equals R0 of 1 plus alpha t, and then we're going to plug and chug. So our resistance, remember we have 125 as our resistance that we saw for before. We're going to do this as 125 ohms equals R0, 1 plus 6 times 10 to the minus 3 times the temperature equals 1800. And that's degrees Celsius. And that one is inverse, so degrees C inverse. You just have to pretend that that's there for now. All right, don't usually write it till the end of the problem. So for this one, we're going to be able to solve through this. And if we solve through this one, we're going to bring 125 on the top, type in our calculator, pull these on the bottom part, equals R0. So R0 is going to equal 10.59. Your book might have something just slightly different than that, but it's close enough. So R0 equals 10.59. This is one of the things that we found. So this is an important thing. So we're going to plug this one back in up here. So if we go up to the top, R0, 10.59. 10.59 ohms. Okay, it's going to go across the board. 10.59 ohms. 10.59 ohms. Cool. So now that we have that, let's look back over here. We have R0, we have the temperature, we have alpha, we need to find R, so all we have to do is this problem again one more time. So R equals R0 of 1 plus alpha t. So again, we're going to plug in our other values now because we don't know what the resistance at room temperature is. So we're going to keep R equals, we do have the R0 now, which is 10.59, equals 10.59 ohms, times 1 plus alpha we do have, which is 6 times 10 to the minus 3 degrees Celsius inverse. And that's also times the temperature, which is what, 20 degrees. Okay, there we go. So now what we have to do is just essentially multiply this out. And if you do, and you plug it into your calculator, you should get, let's see, what do we got? 10.59 is 20, so 11.86 ohms. Okay? So this is the R at the room temperature case. So we're going to plug this back up here, 11.86 ohms. Cool. Let's go back down here. This is one of our answers. So let's just box this again. That looks good. So that's the answer to B. So now we've got the other question of C. And C is determine the current that the filament draws at room temperature. So if I take this as a slight, look, go kitty. I have a cat here in my lap. So let's take this as a slight different. We can do this one in a small amount of space. See if we can see that. Yeah, look at that. All right, so for C, we've got at 1,800 degrees Celsius, we've got B equals IR, and we've got 100 equals I times 125. So remember, this is only for this case, but we have our V, and we have our 125, and we actually already saw for the amps before, but we're going to do it again. I equals 0.8 amps. And with that being said, at 20 degrees Celsius, we're going to do, again, our V equals IR. And then at 20 degrees Celsius, we're going to have 100 equals I times 11.86, which again, we just got from here. And then 11.86, we're going to go to I equals 8.43 amps. So we're going to plug this one in as 8.43 amps. Okay, so that answers now the current that each of these draws. So we have the current of 8.3 amps and 0.8. So a huge amount of current goes through when it's early in the cycle, when it's 20 degrees Celsius. And less current goes through as it gets hotter. So let's look at question D. I'm just going to talk through this one because we don't actually have to solve anything for this. If the current deteriorates when if the filament deteriorates when the current is through it approaches 10 amps, the damage done to the filament is greater than when it is first turned on or later when it arrives at operating temperature. So that's saying there's more damage whenever more current is going through. So where is more current going through? Room case when it starts. So the damage is when you turn on the light switch. When you turn on that filament, that's when the damage happens. That's when you have this large amount of current. The longer you leave it on, essentially, your resistance is going to settle out and you're going to get nice low amperage through there. That doesn't mean it can't break at this point, but it does mean that it's much, much more likely to break at this point. So that's also one of the reasons why when you turn on a bulb or whatnot, it usually breaks more towards the beginning than about halfway through, although it can happen. So I hope that was an interesting problem for you, and let's get back to doing a few more lectures.